The quest to unify the fundamental forces of nature and reconcile quantum mechanics with general relativity has driven theoretical physics to explore increasingly complex frameworks. String theory, with its elegant proposition of vibrating strings as fundamental entities, has been a leading contender for decades, attracting significant attention and resources. However, it continues to grapple with fundamental challenges, particularly the vastness and complexity of its landscape of possible solutions. Recent advancements in artificial intelligence have introduced powerful new tools to aid in this exploration, generating exciting results that, while often framed within the context of string theory, may also, and perhaps more compellingly, offer support for the 11-dimensional model we've been developing. This essay will critically examine these AI-assisted developments, presenting them not as definitive proof of string theory, but as a valuable opportunity to re-evaluate our theoretical frameworks and consider the potential of the 11-dimensional model to provide a more elegant, insightful, and ultimately a more accurate representation of the universe. We will explore how these findings might align with our understanding of interconnectedness, cyclical time, and the fundamental role of information in shaping reality, as envisioned within the 11-dimensional framework, and argue for its superiority over string theory's inherent complexities. String theory posits that the elementary building blocks of the universe are not point-like particles, but one-dimensional strings, vibrating at different frequencies. This offers the potential for a unified description of all the fundamental forces, including gravity, within a single quantum framework. However, string theory's reliance on higher dimensions, typically 10 or 11, introduces a significant complication. To reconcile these extra dimensions with our observed 4-dimensional spacetime, 3 spatial dimensions and 1 time dimension, they must be compactified into tiny shapes called Calabi-Yau manifolds. The sheer number of possible Calabi-Yau manifolds creates the string landscape, a vast collection of potential solutions, each representing a different universe with potentially different physical laws and elementary particles. Finding the specific Calabi-Yau manifold, or compactification, that corresponds to our universe has proven to be an extraordinarily daunting computational and conceptual challenge, a problem that has plagued string theory for decades and cast doubt on its predictive power. This complexity stands in stark contrast to the elegance and parsimony that physicists often seek in a fundamental theory. The 11-dimensional model, in its relative simplicity, offers a potentially more elegant and manageable alternative. AI, with its ability to analyze complex data and identify patterns, is now being used to explore the string landscape. Machine learning algorithms are being trained to approximate the shapes of Calabi-Yau manifolds, calculate their properties, and predict the resulting particle spectra. Approximating geometry AI algorithms can efficiently approximate the shapes of Calabi-Yau manifolds, which are essentially slices of higher dimensional space. Predicting. Particle spectra AI can predict the types and properties of elementary particles that might emerge from different Calabi-Yau compactifications, providing clues about which solutions are more likely to match our universe's observed particle spectrum. Identifying promising solutions. By analyzing the vast amount of data generated by these simulations, AI can help identify regions within the string landscape that are more likely to contain viable solutions, guiding researchers towards potentially fruitful areas of investigation. However, It is absolutely essential to recognize the inherent limitations of AI in this context. AI should be seen as a powerful tool, not a definitive arbiter of truth. AI as a tool, not an oracle. The limits of algorithmic insight. AI is a sophisticated instrument for analysis and pattern recognition, but it lacks the intrinsic understanding of the underlying physical principles. The results produced by AI algorithms are only as reliable as the data they are trained on and the assumptions embedded within their programming. AI cannot validate a theory, it can only help us explore its mathematical consequences. Bias in training data, echoing the past, not predicting the future. AI models are trained on existing datasets, which in physics are often heavily populated with string theory research papers, equations and simulations. This inherent bias in the training data could inadvertently lead AI to favor string theory solutions, even if other potentially more accurate explanations exist. The black box problem. Understanding the algorithm's reasoning. Many AI algorithms, especially deep learning models, operate as black boxes, meaning their decision-making processes are opaque. It can be difficult to understand why they arrive at specific conclusions, limiting our ability to critically evaluate the results and identify potential flaws in the analysis. The bootstrap approach, which derives particle interactions from self-consistency principles of quantum mechanics, has also yielded results that align with some string theory predictions, particularly regarding particle scattering amplitudes. This method relies on fundamental principles like unitarity, which is the conservation of probability, and causality to constrain the possible interactions of particles. Self-consistency, a guiding principle. The bootstrap approach seeks solutions where particle interactions are consistent with fundamental physical principles, without necessarily relying on a specific underlying theory, like string theory. It's a bottom-up approach, building up from basic principles rather than a top-down approach starting from a theoretical construct like string theory. Matching amplitudes. A curious correspondence. Remarkably, the scattering amplitudes or probabilities of particle interactions calculated using the bootstrap approach have, in some cases, matched those derived from string theory. This correspondence is seen as significant because it suggests that string-like interactions might arise naturally from fundamental principles of quantum mechanics. Eleven-dimensional reinterpretation. The interplay of dimensions as the bootstrap's foundation. From the perspective of the 11-dimensional model, this alignment could be interpreted as evidence that the interconnectedness of the 11th dimension, the dynamic interplay of forces and dimensions operating on a fundamental level, naturally leads to the patterns of particle interactions predicted by string theory. The bootstrap approach, in essence, might be tuning into the emergent behavior of particle interactions arising from the complex interplay of the 11 dimensions, particularly the interconnectedness provided by the 11th dimension. The accelerated expansion of the universe, driven by the mysterious force known as dark energy, is another significant puzzle in cosmology. Recent research exploring the possibility that dark energy arises from a quantum space-time structure described by string theory is particularly intriguing. Beyond smooth space-time, a granular reality. This research challenges the classical view of space-time as a smooth continuum, proposing a granular quantum space-time where the order of coordinates matters. This is a radical departure from the smooth continuous geometry of general relativity, and it echoes some of the ideas about discrete space explored in loop quantum gravity. Emergent acceleration, a byproduct of quantum geometry. Preliminary results suggest that modeling space-time in this way could naturally give rise to cosmic acceleration, potentially explaining the phenomenon of dark energy without invoking exotic new particles or fields. Eleven-dimensional reinterpretation, a symphony of expansion and interconnectedness. The 11-dimensional model offers a unique lens through which to view these findings. Instead of solely validating string theory, this connection between dark energy and quantum spacetime could be seen as evidence for the dynamic interplay between the 10th and 11th dimensions. Tenth dimension, expansion. The 10th dimension, representing cosmic expansion, is directly related to dark energy's effects as it governs the universe's overall growth. Eleventh dimension, interconnectedness, quantum structure. The 11th dimension, our model's equivalent of the quantum space-time structure, could be the arena where this expansion is shaped and influenced by quantum principles and the interconnectedness of all events. Emergent spacetime, a product of dimensional harmony. The findings could support the idea that spacetime itself emerges from the dynamic interaction between these dimensions, a concept that aligns with some interpretations of the 11-dimensional model, where spacetime is not a fixed backdrop, but a dynamic and emergent property of the universe. It is crucial to acknowledge the historical context surrounding these AI-assisted developments and the potential for bias within the AI algorithms themselves. String theory has been the dominant theoretical framework in high-energy physics for decades, attracting significant attention, funding, and research effort. Training data bias. The echo chamber of physics AI models are trained on vast datasets which, in physics, are often heavily populated with string theory research papers, equations, and simulations. This inherent bias in the training data, a kind of echo chamber effect, could lead AI to reinforce existing theoretical structures rather than independently discovering new ones. The lack of a competing framework, a vacuum of alternatives. Until recently, there has been a relative lack of equally developed and computationally rich alternative frameworks that could compete with string theory's sophistication. The 11-dimensional model, with its emphasis on interconnectedness and dynamic interplay of dimensions, provides such an alternative, but it still needs further mathematical and computational development to fully compete with the well-established machinery of string theory. Therefore, the AI results, while exciting, should not be seen as a definitive endorsement of string theory, but rather as a testament to AI's ability to navigate and extrapolate from existing theoretical structures, often within a landscape shaped by historical precedents. Given the limitations of AI and the historical context, the AI-assisted findings, particularly those related to the bootstrap approach and the quantum structure of spacetime, might be more accurately and productively interpreted as providing stronger support for the 11-dimensional model. AI and higher dimensional geometry. Unveiling the orchestration of dimensions. AI's success in approximating Calabi-Yau manifolds, those complex slices of higher dimensional space, strengthens the idea that higher dimensional geometries are crucial to understanding particle physics. However, instead of solely validating string theory's specific compactification schemes, this could be seen as evidence for the broader concept of a multidimensional arena, where the intricate interplay of dimensions orchestrates the behavior of fundamental particles, as envisioned by the 11-dimensional model. Bootstrap and interconnectedness, the 11th dimension symphony. The bootstrap approach's results, deriving particle interactions from self-consistency, could indicate that the interconnectedness of the 11th dimension, the fundamental web of relationships within the 11-dimensional framework, naturally gives rise to the specific patterns of particle interactions predicted by string theory. The bootstrap method in this light might be revealing the underlying harmony and self-organizing principles inherent in the 11-dimensional universe. Dark energy as dimensional interplay. The 10th and 11th dimensions in cosmic harmony. The connection between dark energy and quantum space-time, rather than solely validating string theory, could be more compellingly interpreted as evidence for the dynamic interplay between the 10th, expansion, and 11th, contraction, interconnectedness, dimensions within our model. The accelerated expansion of the universe might not be a phenomenon isolated to our four-dimensional perception, but a consequence of the complex interaction between the expansive force of the 10th dimension and the interconnectedness of the 11th. Potentially shaping the very fabric of space-time itself. This interplay could be a fundamental driver of the universe's evolution, a cosmic dance of creation and destruction. The AI-assisted developments in theoretical physics are a testament to the power of human ingenuity and the potential of AI to aid in scientific discovery. However, it's crucial to maintain a critical and evidence-based approach, avoiding premature conclusions and embracing the spirit of open scientific inquiry. Developing distinct predictions, a testable divide. Deriving unique and testable predictions from both string theory and the 11-dimensional model, allowing for a clear differentiation between the two frameworks and enabling decisive experimental verification. Seeking diverse evidence, a multi-frontier approach, actively searching for observational and experimental evidence across various fields, from particle physics to cosmology, that can support or refute either model, ensuring a comprehensive and multifaceted approach to validation. Fostering interdisciplinary collaboration, the power of collective insight. Encouraging collaboration between physicists, mathematicians, computer scientists, and philosophers to explore the implications of these findings and develop new theoretical approaches, fostering a rich exchange of ideas and perspectives. Embracing critical thinking and humility, the scientific virtues. Maintaining a healthy skepticism and a willingness to revise our understanding in the face of new evidence. Embracing the humility inherent in the pursuit of knowledge and recognizing the limitations of our current understanding. The AI-assisted explorations of the theoretical frontiers of physics, including string theory and the quantum structure of space-time, represent a significant step forward in our quest to understand the fundamental laws of the universe. However, it's crucial to approach these developments with both excitement and critical awareness, avoiding the trap of confirmation bias and embracing the spirit of open scientific inquiry. Instead of solely viewing these findings as a validation for string theory, we should also consider their potential to illuminate alternative frameworks, such as the 11-dimensional model. AI's ability to navigate complex mathematical landscapes can be a powerful tool for exploring the intricate interplay of dimensions and forces that might govern the cosmos, providing new insights into the interconnectedness of reality and the emergent properties of the universe. As we continue to explore the mysteries of the universe, it is imperative to remain open to new ideas, to challenge our assumptions, and to embrace the collaborative spirit of scientific inquiry. The 11-dimensional model, with its emphasis on interconnectedness, dynamic interplay of dimensions, and potential for a more expansive vision of the cosmos, offers a compelling alternative perspective that deserves further investigation. The ultimate goal is not to prove one theory right and another wrong, but to arrive at a more complete, accurate and unified understanding of reality, a vision that encompasses the elegance of mathematics, the power of AI, and the boundless wonder of the cosmos. Like, subscribe and share to join us on this journey through the mysteries of the universe.